going to take a look at the classic bell-shaped curve that we see in data. So, okay, that's what I said. Oh. When you're looking at stats, we do see a particular pattern a lot, and it's this bell-shaped curve. Now, that's not exactly bell-shaped, but it has that feel to it where it's rising to a point and it's coming down. So it's that sort of pattern I'm talking about. We see that a lot. Now, so what we're looking for is in the distribution, the mode or the highest frequency will be somewhere in the middle of the values. Okay, well, yeah, somewhere in the middle. The distribution is ideally perfectly symmetrical, but it'll look almost symmetrical. Maybe. Now, a perfectly symmetrical distribution would have the feature where the mean is equal to the median, is equal to the mode. All three of those would end up being the same thing. So that's your true classic bell-shaped probability density function. Okay. Now, ours obviously is not symmetrical, but like I say, in real life, a lot of them don't turn out to be perfectly symmetrical, but they're pretty close. It has that sort of feel to it. Basically, we're looking for this idea. The frequency density tails off fairly rapidly. So you've got this nice hump, but then it comes down to zero pretty quickly. The normal distribution is the classic, perfectly symmetrical bell-shaped curve. We call that the normal distribution. And its probability density function, it's a beauty. There it is. 1 on sigma root 2 pi e to the power of minus x minus mu squared on 2 sigma squared. So it's an exponential function. So mu is the mean, sigma squared is the variance, same as normal. So it has a normal distribution, and the way we write it down is like this. X, what do they call those? Tildes? So, you ever heard of tilde? Is it? Okay, there you go. So we have a tilde, and so the n is standing for normally distributed. So we're saying our random variable is normally distributed with a mean of mu and deviation, a variance of sigma squared. So some characteristics of our normal distribution. There it is, the classic shape. Okay, well, it's an even function. So function x equals function negative x. Its maximum turns out to be the mode, turns out to be the mean, and as I said before, it turns out to be the median as well. And so the curve will be symmetric about that. Again, even function. It actually has a point of inflection at the first deviation. So at x plus or minus sigma, they will be points of inflection. So that's where it changes its concavity. Now, we're really interested in the standard normal distribution. And that's where the average is 0 and the variance is 1. And that's where we start looking at, z-scores. That's where they all come from. It's treating things like a standard normal distribution. So z is representing this distribution. It will be normally distributed, average is 0, variance of 1. And of course, if the variance is 1, that also means the deviation is 1 as well, because square root of 1 is 1. And so there, the formula gets a little bit simplified now, because if I sub those in for mu and the deviation, we get 1 on root 2 pi, e to the minus z squared on 2. So how do we calculate these probabilities? Well, theoretically, we would calculate it via the integral. Remember, this function here, so phi, that's a capital phi, is we're representing to be the cumulative distribution function. So the area under that curve, starting from the left-hand side, going up to whatever point we're interested in. The curve looks like this. That would be the cumulative distribution function of the normal distribution. We saw that somewhere before. Does anyone remember? There's a question we did, it was last year. It was in Perms and Coms. The birthday problem. Remember the birthday problem? How many people have the same birthday in a room? And we plotted it and it ended up being like that.
And then after that.
Yeah. Okay, so here it comes, the note about integrating it. No, I can't do it. Not with the functions we know anyway. Right, so just using algebraic functions, trig functions, exponential functions, nah, you can't do it. So what we do is we basically use a table of values and just look it up. That's the way we do it. But remember, it's representing the area under the curve. You could estimate it with the trapezoidal rule, and that's basically how they came up with the table of values. Okay? But as this is standard, when you see the table of values, there's an example of one. You notice I haven't put any of the negatives there, but that's because it's an even function. So I know it'd be the same on the other side as well. And so probability of x equaling 0, or z equaling 0 in this case, would be a half. Because that's right in the middle. We said that was the median, that was the mode, that was the mean. So 50% of the scores would be less than 0. If I was to read off 0.11, so what's the probability that x was, or z in this case, z is less than or equal to 0.11, then it would be 0.5438. And, there's the example I did. If I want a 0.25, then there's 0.2, and there's 0.05, bang. So that one will be 0.5987. Your calculator will do it, by the way, and I'll show you in a sec how we can use a calculator for this a lot quicker. So how do we manipulate the table then to get our answers? So it's what we just said. If we want to find probability z is less than or equal to some amount, it's just simply looking up that value on the table, the cumulative distribution. So if I wanted to work out negative z, it's on the other side, then it would be 1 minus going up to positive z. Reason for that, let me draw a curve here. So that negative z, that would be the area we're looking for, but that would be exactly the same if I went symmetrically as that area there. So I'm saying, hey, it's all of this 1 minus going up to z. So that's what that's saying. So if we want to work out the negative ones. If we wanted to work out greater than or equal to, then, well, that would just be negative z. Want to work it out between two values? Then it'll be z2 minus z1. We'd read off those values and subtract. And absolute value, so if I was going in between, minus 0.5 and 0.5, then it would be twice the z1, but then subtract 1. Most of us have the 100 AU, is it? Mode 3, all clear. Calculators in stats mode. I think we know how to do that. I hope we're okay with that bit. That's how you put your calculator in stats mode. Shift 1, 5. 5, I think it says this is just DIST, which stands for distribution. So we're interested in looking at distribution. So shift 1, 5. It then comes up with a menu to find P, Q, R. I think there's a fourth one there as well, isn't there? But I didn't worry about that one. So P will find the phi function going up to that value. Q will find between 0 and that value. And R will find the right-hand side. To be honest, I just use the P one and then play around with these. So, if you try it, we should get this answer. Go 1 minus the 0.25, or the phi of 0.25. So if you plug in the phi of 0.25, you should get 0.5987. 1. Yeah. So we're clear on that. I mean, that's going to be the quickest way of doing it, rather than looking up a list of tables and doing that. So let's see if we can. We're going to find, don't look at your sheet, that would be cheating. The probability of z is less than or equal to 0.44. Play with your calculator. Those that brought their calculators. Right, those that have got calculators, the 100 AU, hopefully you did get your 0.67003. If we wanted to work out minus 0.81, well, we don't have to play around with the 1 minus and all that. We can just type the 0.81 straight in. And you should get the same as if I had done, the 0.20897, which of course is the same as if I just typed it straight in. in between two values. So it'll be the 0.94 minus the minus 2.34. That works out to be 0.816748. And the absolute value one, well, the formula we said to do it was twice the 1.15 minus 1, which is 0.7496. Did I do it the other way? No, I didn't. The other way you could do it would be to work out what the minus 1.15 is, subtract that twice from 1, because all of them are going to equal 1. So if I chop off that tail and chop off that tail, I should get in between. Or, I suppose the third way you could do that one is you could just find 1.15 and then subtract the negative 1.15. That would work too, wouldn't it? That would get the in between the two values. All right. The empirical rule might not have been called this back in year 10, 9, whatever it is, but you'll know what it is. It's this. Approximately 68% of the data falls between one deviation either side of the mean. They're 95% for 2 deviations, and then virtually all of them for 3 deviations. You get 99.7. So that's formally known as the empirical rule. All right, we'll add those in.